Okay, in this video we're going to be continuing on in the endocrine system, starting at why is the pancreas both an endocrine gland and an exocrine gland. So remember that endocrine glands do not have ducts, and they just release hormones out into the interstitial fluid that's going to be picked up by the blood and then transported around in the bloodstream. Exocrine glands do have a duct, and they release their products onto body surfaces, typically mucous membranes, sometimes cutaneous membranes, but in the case of the pancreas, onto a mucous membrane in a duodenum of the small intestine. There are two discrete-ish structures within the pancreas. So there's these little sort of balls within the pancreas. They are called pancreatic islets. They used to be called islets of Langerhans. They're changing the name over now, so pancreatic islets. The pancreatic islets contain two different types of cells, alpha cells and beta cells. The islets are not connected to a duct, and the alpha and beta cells secrete hormones that help regulate blood sugar levels. So the islets are the endocrine portion of the pancreas. Outside of those islets, we have these cells called acinar cells. Those cells are connected to ducts that are going to shuttle digestive enzymes into the small intestine to help us digest our food. So again, two discrete functions that are completely separate from each other, and so it's really part of both the digestive system and the endocrine system. So coming back to those pancreatic islets, this is a slide of a pancreas. So hopefully you guys can see there's this ball going on here. Inside of that, with these pink and these blue cells, that's the islet. Outside here, this is where we have those acinar cells that are the digestive part. So we're not going to talk about those in this chapter in any more detail. We're going to be focusing on the islet. The pink cells in here are called alpha cells. The alpha cells secrete glucagon. Glucagon is the antagonist to insulin, so it does the opposite thing. The blue cells here in the islet, those are beta cells. The beta cells produce insulin. So the alpha cells and the beta cells are in the islet. They produce two different hormones. So some versions of the book have this picture, some don't. The most current edition, I believe, does have this picture. I've added which cells produce which hormone to this picture just to, again, tie it to what we were kind of just talking about. This shows you the two hormones that have sort of the most direct response on blood sugar level, but of course there are other hormones that are also going to help regulate blood sugar. Now, your body would like to maintain your blood sugar level somewhere between 90 to 100 milligrams per deciliter. It can get outside of that and still be considered within range, but your body's happiest when it's between 90 and 100. If your blood sugar level gets to be too high, you have chemoreceptors that detect that it's too high. Those chemoreceptors alert the brain, specifically the hypothalamus. The hypothalamus says, hey, our blood sugar is too high, pancreas, you need to do something about that. The beta cells in the pancreas start to produce insulin, and the insulin is going to do several different things in several different types of cells. In the liver, it is going to help the liver pick up glucose from the bloodstream and dump it into the hepatocytes in the liver, where the hepatocytes are going to convert the glucose into glycogen, which is sort of like the human version of starch. So that's how we're going to be lowering our blood sugar, is predominantly turning the sugar into glycogen, which is again sort of like our starch. Other body cells are also going to be picking up the blood sugar and putting it into the body cells. That's going to be lowering your blood sugar by taking it out of blood and putting it into cells. A lot of those cells are going to start using that sugar to do ATP formation, upping metabolism. Some of them are going to make their own glycogen. The liver is the best at that glycogen storage formation. Skeletal muscle is also pretty good at it, however. All of those things are going to help lower our blood sugar back down and get it where it's supposed to be. On the flip side, if your blood sugar gets to be too low, once again, chemoreceptors detect that. The hypothalamus says, oh no, our blood sugar is too low, pancreas, fix it. This time though, the alpha cells secrete glucagon, so different cells still in the pancreas, different hormone, different response. This time we're going to do the exact opposite in the liver. So the glucagon gets released. It tells the liver to break down the glycogen that the insulin had told us to make. When we break down the glycogen, we're going to be releasing a bunch of glucose, and that glucose is going to get released into the bloodstream to help raise our blood sugar back up. At the same time, that glucagon is also going to tell a lot of your other body cells to stop using glucose as a primary energy source and to start using other things, because some of your cells, especially brain cells, they have to have glucose. They don't have the option of using other energy sources. And so the cells that can switch between different molecules, they're going to switch and start using fats or proteins or whatever other precursor metabolites they might be able to use, so that the brain doesn't run out of the sugar that it needs to be able to use. All of those things are going to help keep the blood sugar where it's supposed to be, so that your brain has the blood sugar that it needs to have to keep things working like it's supposed to. So that's essentially how those two hormones are going to work. Okay, so hitting on those in a little bit more detail. Glucagon's effect is to help raise blood sugar levels. So if you haven't eaten in a little bit, glucagon is what keeps your blood sugar where it's supposed to be. Now, earlier I had mentioned big G words in a previous video. Here are some of the big G words that glucagon helps to do. Glycogenolysis. Lysis means to split. Glycogen is glycogen. So remember, glycogen is like starch, but for humans. So we're going to split glycogen. When we do that, we're going to release the glucose that had been in glycogen. That's going to help us elevate our blood sugar level. That happens a lot in the liver, but any of your cells that have glycogen stored in there, those cells are going to do some glycogenolysis. Gluconeogenesis. Breaking that word down, which I think we did that earlier. Genesis is to make. Neo is new. Gluco is glucose. So we're going to make new sugar from things that weren't sugar. So we're going to try to convert proteins into carbohydrates. We're going to try to make lipids into carbohydrates. And that's going to help us get our blood sugar level up to where it's supposed to be. So both of those two things are going to help us keep our blood sugar level where it's supposed to be. If you secrete too much glucagon, your blood sugar level is going to get too high. The fancy word for that is hyperglycemia. If you don't secrete enough of this, you can end up with hypoglycemia. This is really pretty easy to fix. Just eat something. Okay, insulin. Insulin, again, is the antagonist to glucagon, so it's going to lower your blood sugar level. I don't know why, but a lot of students get this one wrong on a test. They know that insulin has an effect on blood sugar level, but for some reason they seem to think it does the opposite of what it does. So if you're one of those people who thinks it does the opposite, I don't know, highlight it, make yourself a flashcard or something, make it the screen on your phone. It lowers your blood sugar level. It does not raise it, lowers it. The way that it tends to do that is it opens glucose channels on most of your cell's plasma membrane so that cells are going to pick up glucose. That means the glucose is leaving your bloodstream and going into your cells. Does also promote that glycogen formation that we had talked about earlier in the liver and your skeletal muscle and things like that. Says that here on this slide. So here's just some pictures to sort of get that idea going in your head. So this is one, and by this I mean this is one glucose molecule. So it's this little hexagon thing that we have going on right here. This is a glycogen molecule. Each of those little bitty black hexagons is one glucose that makes up a glycogen as a whole. So you can see how putting glucose into glycogen is going to lower your blood sugar level. It's because you're tying the glucoses up in this big, giant glucose storage molecule that is called glycogen in your body. And again, your liver is not the only organ that does that. It's just one of the organs that does it the best. Okay. If you secrete too much insulin, you're going to lower your blood sugar too much. That's going to result in hypoglycemia. This is not super common on its own, but you will find diabetics who either inadvertently over-inject themselves with insulin, or if they have an insulin pump, their pump malfunctions and it gives a person way too much insulin, and as a result their blood sugar level plummets. That's how you tend to see this as a problem, is a diabetic who's overdosing on insulin, essentially. Not saying you can't see it as its own disease state, it's just you see it more often in people who are injecting and they overdose on it. Okay. Hyposecretion or hypoactivity of insulin is one of the most common endocrine disorders out there. So, earlier we had talked about diabetes insipidus. Let me sort of back up and sort of hit on some words that are going to pop up in the notes later. The 3 Ps. Polydipsia, polyuria, polyphagia. When people end up with diabetes, the most common symptoms there are they're going to come in and they're going to say, oh my God, I am peeing all the time, and I am thirsty all the time. And very often they will also say, I'm hungry all the time. Like, I just ate and I am still hungry. Those are some of the most common symptoms that go along with diabetes. Whenever a person comes in experiencing those 3 Ps, especially the polyuria and the polydipsia, that's the peeing and the thirst, diabetes in general pops into mind. And from there we have to figure out, is it because of ADH that we talked about in a previous video, or is it because of insulin and blood sugar issues, which is diabetes mellitus that we're coming to now. So remember in a preceding video I had told you that way back in the old days, back before there were chemical detection strips or computers that could read what was going on in urine, it was a nurse's or doctor's job to taste the urine and figure out if the urine tasted sweet. If a person is peeing a bunch and the urine has no taste, that's not an insulin issue, that is not a blood sugar issue, that was an ADH issue, and that was the insipid, no-taste urine of diabetes insipidus that we talked about in that preceding video. If the person, though, has the increased thirst and increased urine output, and the urine has a sweet taste to it, that's because the person is excreting sugar in their urine. That is a sugar issue, that is an insulin issue, that is a diabetes mellitus issue. Now, typically speaking, when a person says they have diabetes mellitus is usually what they're talking about. Because again, this is the most common endocrine disorder that is out there. What you need to remember though is this is not the only type of diabetes that is out there. And so you just need to keep that in mind as we go through them. Now with that, there are a couple of different types of diabetes mellitus, and they are caused by different things and they are treated differently. Type 1 versus type 2 diabetes mellitus. They both result from insulin not doing what it is supposed to do, essentially. We're going to start with type 1. Type 1 used to be called juvenile onset or childhood diabetes. It really should not be called that anymore, which is why it is not. They are changing the name over to insulin dependent, and it's called that because these people are dependent upon insulin through injections or through pumps or through a pancreatic transplant. What happens here is we have now learned this is an autoimmune disorder where the immune system destroys the pancreas, and it's been happening in the background of their life for years and nobody noticed. They showed no symptoms for a very long time, and then all of a sudden, poof, no pancreas, no insulin, and so as a result they have lost the ability to control their blood sugar level. Since they do not make insulin, this is relatively easy to treat. We need to give them physiological doses of insulin. The problem with that is the person needs to monitor their blood sugar level and take the insulin when their blood sugar level gets to be too high. So these are the ones that have test strips. They're supposed to be monitoring their blood sugar. When it gets to be too high, they're supposed to either inject the insulin or they have a pump. The pump is supposed to monitor their blood sugar, and when it gets too high, the pump is supposed to inject them with insulin. Again, pumps do have a failure rate, but that's its own separate sort of an issue. So that's what's going on with type 1 diabetes. Their pancreas is broken. They do not make insulin. They have to take insulin through injections or through pumps to fix their problem. Type 2 diabetes is a whole other story. What happens here is the person's blood sugar stays so high that the person is constantly releasing insulin and the body is sick of hearing from it. And so the receptors become resistant to insulin. So this is insulin resistance, not you don't make insulin anymore. So that means giving the person insulin is not going to help them because they are already making insulin and the body is not paying attention to it anymore. So these are the people that we treat with a different class of drugs like metformin or things that are along those lines. So this is more of a metabolic syndrome where there's inflammation that comes into play. There's poor diet where the person is, again, constantly having elevated blood sugar because they are not allowing themselves to go into a fasting state between meals. And so it tends to be associated more with overweight and obese patients, people who don't exercise like they are supposed to. And in fact, there are a lot of people out there who have cured themselves of their type 2 diabetes with proper diet and exercise. So, whole different ball of wax when it comes to type 2 diabetes, essentially. Now, your book doesn't really talk about HbA1c very much, or just A1C is what most doctors tend to call this. So I want you guys to just get this separately in your notes. When a person, especially a person with type 2 diabetes, is going in, they will very often know they've got their appointment coming up, and they will sort of clean up their diet in the few days before they're going in. So it'll look like their blood sugar level is good when they go in for their doctor's appointment. But in the months before that doctor's appointment, they hadn't been doing anything right. HbA1c is a lot harder to trick than your blood sugar level right now. What it's showing you is what your blood sugar level has been for the past couple of months. And you can't lie about your A1C level. And so you can't just trick the doctor by controlling your blood sugar level over the past few days, because they will be able to tell that in the months before that, you had still been eating donuts for breakfast, you had not been regulating your blood sugar level. And so A1C is a test that gets run all the time for people who have diabetes mellitus to help tell the doctor, have you been compliant in trying to deal with your blood sugar level, your proper diet, and your exercise, or are you not being compliant? As it turns out, there are a lot of people out there who have diabetes and they are not at all compliant with trying to watch what they eat and exercise. And there are really horrible outcomes for people who do not try to regulate their diabetes when they have it. So next slide is going to be disturbing. Not regulating your blood sugar has huge impacts on every single body system that you have in your body. And if you work in the nursing industry or the medical industry for any length of time, I guarantee you will meet a diabetic who is missing some part of their body, usually a lower extremity, because what will happen is one of the first things that goes in a person with diabetes is the sensation in their feet. It's called neuropathy. They will end up with like some poorly fitting shoes. The shoes will give them a blister. They don't know that there's a blister. The blister will end up getting infected, but they won't know that it's infected because they can't feel it. And quite frankly, they're overweight enough that they probably can't see their feet very well, so they don't even know there's a problem going on. Before they realize there's a problem, they've really lost a toe already. And so we need to amputate that toe. Now, how does it get as bad as in this person? I have no idea. You should have noticed you had a problem way before here. How was this person even walking on that foot? I got no clue. But this is unfortunate. This is an extreme case, yes, but this is something that you will see is people coming in walking around on feet that you're like, holy moly, how did you even get in here? Because 4 of your toes are black. One of them has fallen off. How did you even put your shoes on and not notice that you had a problem? Poorly managed diabetes ends up producing a set of chemicals that are called ketones. Ketones are acids. Those acids end up damaging the kidneys as well. And so people that have uncontrolled diabetes will also very often have kidney damage leading to kidney failure. And so they will need kidney transplants. And guess what? If you are not managing your diabetes very well, you are not going to be top of the list for a kidney transplant unless you have a family member who is willing to donate to you. So there's just a lot of problems that go along with not managing diabetes very well. And so it's important that patients get educated if they are diagnosed with diabetes and how they can manage it and what will happen to them if they do not manage it. Okay, so that was me preaching, I guess, for a little bit. This has got your ketoacidosis stuff on this slide. So next up, your 3 Ps. Mentioned them all earlier. Polyuria is you pee too much. Polydipsia is you're thirsty. Honestly, those two things go together because if you're peeing a lot, of course you're going to be thirsty. Polyphagia you don't see as much in diabetes insipidus. That one's really more for diabetes mellitus. And I really love the quote that your book says right here. the person will feel like they're starving to death, and that's because the cells really are. The cells are not able to open the glucose channels without insulin, so the blood sugar is sky high, and all the sugar is available for the cells, but the cells can't let the glucose in, so every cell in the body is essentially starving to death. And so the person feels like they are starving to death. That's what polyphagia is. All right, I'm going to go ahead and real fast finish up this chapter. Everything else is really pretty self-explanatory, so I'm just going to do it real fast. I say. I guess I don't have slides for hyper and hypo. So hypoglycemia is low blood sugar. Different books give you a different value for that. I think your book says less than 70 milligrams per deciliter. Your body really starts to get unhappy if it's less than 90, but doctors aren't going to be unhappy unless it's less than 70. Hyperglycemia is elevated blood sugar level. I think your book says greater than 120 milligrams per deciliter. Again, your body starts to get unhappy if it's over 100 and start to deal with it, but doctors aren't going to be unhappy unless it's over 120. All right. Gonads. So both sexes do have gonads. The testes are the gonads for cis males. The ovaries are the gonads for cis females. The gonads are the primary sex characteristics. They are, and when I say primary sex characteristics, what that means is that is what determines the biological sex of an individual. It is what produces the gametes, which are the sex cells for that individual. In terms of the sex hormones, I just had slides out of order is what I've got going on. What you need to know for estrogen is that's the primary sex hormone for women. I see I have things all out of order. Hey, I did get my numbers right at least. So there was your hypo and hyperglycemia. Said this just a second ago, so we should be good there. Okay, estrogen. Primary sex hormone for women. It contributes to the secondary sex characteristics for women. Helps with gamete production, helps with the development of breasts, basically helps with everything that makes a cis woman a cis woman. Progesterone is more of a uterine hormone. It helps with uterine development. It helps with the uterine cycle, which is also sometimes called the menstrual cycle. It helps with maintenance of a pregnancy. We will talk more about both of these hormones when we get to the reproductive system later on. The testes produce testosterone. One thing you do need to keep in mind is, again, the adrenal cortex does produce testosterone in both sexes, but the testes also produce way more testosterone in men, so men get way more testosterone than women. Testosterone is sort of analogous to the estrogen in females, as this is the primary male sex hormone. Contributes to male secondary sex characteristics. From there, you've got a bunch of other organs that they're not, how do I want to say this? They're not like true endocrine hormone, true endocrine glands, but they do release hormones. So technically they do have an endocrine function. Starting with the heart. The heart releases ANP, that's atrial natriuretic peptide. Pretty much every hormone that we have talked about, from aldosterone to ADH, has been in charge of trying to keep your blood pressure up. From an evolutionary standpoint in humans have had more of a problem with low blood pressure, not so much a problem with high blood pressure. ANP is the one hormone that counteracts aldosterone and ADH. So it helps to reduce blood pressure. The problem is it also adapts to high blood pressure, so it's not good for long-term hypertension and trying to help control that. The stomach produces gastrin. The gastrin helps the stomach secrete everything that it needs to help you digest food. That includes gastric juice, which is, hydrochloric acid, mucus, and then some of the chemicals necessary to help you digest food. We'll talk more about that in the digestive system. Skipping around in no particular order. The placenta is going to secrete some hormones that are responsible for the development of pregnancy. That does include estrogen and progesterone that we mentioned earlier. But kind of more importantly, one that we hadn't talked about yet, human chorionic gonadotropin, or HCG. That hormone only gets produced when a woman is pregnant naturally. There are unnatural times where that hormone might get made, but it tends to be a cancer event when it's produced when a person is not pregnant. Thymus gland produces thymosins. Those are going to help with the development of T lymphocytes, which are a type of white blood cells. The thymus gland we're going to talk about more when we actually get to the lymph and immune system. This gland is a unique gland because when you're born, for the first year of life, it gets bigger and it starts to develop. And then after that, it actually starts to atrophy and get smaller. This is one of the reasons why as you age, your immune system gets worse. It's because the thymus gland degenerates, and by the time you're in your 50s and 60s, since you don't have it, your T cells just aren't as strong as they used to be, essentially. The kidneys produce renin. Renin is going to help get converted to a couple of different hormones called angiotensin and angiotensin 2. And then angiotensin 2 is going to help stimulate the release of aldosterone. Both angiotensin 2 and aldosterone are going to help raise blood pressure when you get dehydrated. Erythropoietin, or EPO, that one stimulates the bone marrow to churn out red blood cells faster. We will talk about both of those hormones in later chapters as well. The skin produces cholecalciferol, which is a precursor to vitamin D. We talked about that in response to sunlight way back in the integumentary system. Liver and kidneys help convert that into actual active vitamin D. Adipose tissue produces leptin. Leptin is responsible for helping you feel full after a meal. That's what satiety is. It also helps to just kind of regulate how fast your metabolism is burning energy for you guys. I think that's everything in that little table. So after that, you just have some related clinical terms. One related clinical term. What I want to mention about that thyroid storm that it mentions there, it kind of goes back to almost all of your hormones work off negative feedback. Oxytocin does not. That was the one that is supposed to be secreted through positive feedback responses. Thyroid storm is essentially the thyroid hormone starts to work off positive feedback instead, and it can end up killing you. And so that's why positive feedback sucks. We are not supposed to do things that way. After that, you have Latin roots. Remember, those are in the back inside cover of your textbook. And then unique for this chapter, because it is so important for understanding homeostasis as a whole, you have normal blood levels of certain substances. And I said you can find these values in Appendix F in your textbook. I will go through them really fast. Blood oxygen saturation should be between 95 to 100%. Your book says 95 to 98, but 95 to 100 is more realistic. Blood pH, 7.35 to 7.45. Blood glucose, 70 to 120 milligrams per deciliter. Blood osmolality, 280 to 300 milliosmoles per liter. Or kilogram, same thing really. Blood potassium, 3.5 to 5.5 milliequivalents per liter. Blood sodium, 135 to 145 milliequivalents per liter. Hematocrit should be somewhere around 45%. It's usually about 47-ish for men, 45-ish for women, so it does vary from sex. It also varies depending on where you live and a bunch of other things. We'll talk about that more in a later chapter. Urine osmolality should be between 50 to 1200 milliosmoles per kilogram. Urine potassium between 25 to 120 milliequivalents per 24 hours. Urine sodium 40 to 220 milliequivalents per 24 hours. And urine specific gravity 1.001 to 1.035. After that, you're pretty much done with this chapter.